This is my video report for Lab 4 Circuits and Capacitors. A quick overview of this video report. I'll introduce the experiment, and then the physics principles and simulations, and then calculations and data collection, and then conclude with further questions. The goal of this lab was to deepen our understanding of Ohm's law and the loop and node rules for circuits by modeling various circuits in an online PhET simulation and recording data about voltage, current, and resistance. We simulated various given scenarios in the simulation, like the one shown on the left, to examine the relationship between voltage, current, and resistance, and then we looked at an RC, or resistor capacitor circuit, and took data on the voltage over time as the capacitor in the circuit discharged to calculate the time constant. My experimentally calculated time constant came out to be around 6.25 seconds, while theoretically I calculated it to be 6 seconds. Some important underlying physics principles in this lab are shown here. Ohm's law describes the relationship of voltage equaling the product of resistance and current. We can also see the relationship between resistors when in series, where you can add the resistances, versus in parallel. We have to add the reciprocals. We can also look at the loop rule for circuits, which describes the phenomena that when going around a closed loop in the circuit, the sum of voltage differences around the loop must equal 0 when you complete it. And then the node rule explains that current going into a node, like an intersection here, must equal the sum of current flowing out of the node. So we have our first simulation, which was a simple series circuit. Since the resistors are in series, we can add them together and treat them almost as one resistor with a total resistance of 147 ohms. Using this value, we can calculate the current to be V over R, or 0.02 amperes, which we confirm with the simulation's calculated value. It's worth noting that reversing the ammeter does not affect this reading, as current is still flowing in the same direction. If we replace the ammeter with a voltmeter, we break the closed circuit path and thus have a current of 0 amperes. And then if we're measuring potential difference values along the circuit when it's closed again, we can see a voltage drop across sections of wire comes out to be 0 since there's only current flowing through these and no changes in resistance. But we can see a voltage drop across items which do have resistance, which is unsurprising since we know V equals IR and voltage will change if resistance does. If we go along the entire circuit in a closed loop, our potential differences should sum to 0. And looking at this graph I made, we can see that passing through the batteries causes an increase to 3 volts, and then passing through the resistors brings that back down to 0. If we place an ammeter in parallel to the 100 ohm resistor, we create a new path in the circuit with essentially 0 resistance. So the current is redirected there, which renders the 100 ohm resistor influential and makes it so that the current is roughly 0.06 ammeters, since now our Ohm's law equation for the circuit only factors in the 47 ohm resistor. Now we'll look at our RC circuit. When we connect the circuit, initially the light bulb shines brightly, but over time, as charge builds up on the capacitor, the bulb dims. The charges on the capacitor are not flowing through the circuit, which is why the bulb gets dimmer. If we disconnect the battery, the capacitor will begin to discharge. The voltage across the capacitor decreases, and again, looking at V equals IR, this means the current begins to increase, and the bulb will progressively get brighter since charges are flowing through the circuit again. When comparing two bulbs of different resistance values, we can see that it takes longer to charge and discharge a bulb of greater resistance. We can actually calculate a value for the time constant with the equation shown on the left here. I recorded values for time and voltage over a 20-second interval in Excel, and then created a graph of the natural log of the voltage drop at some time t over the initial voltage drop. The slope of that came out to be negative 0.16, which gives a time constant RC value of 6.25 seconds. This is pretty close to the calculated RC value of 6 seconds, considering the high probability of error with accurately recording the times while stopping and starting the simulation. In real life, equipment can be faulty, and especially with ammeters and batteries, you cannot assume zero resistance for these like you can in a simulation. So with a real ammeter, we'd have to factor in non-zero resistance, and then overall we'd have a greater resistance value and thus a smaller current value since voltage would stay constant. If we used a real battery, we'd also have to consider its resistance. So unlike in the simulation, the battery would not charge the capacitor immediately. You'd have to wait some time for it to fully charge.